Hello guys, this is 4.7 logistic growth. So this is another type of growth model that we are going to look at. So let's actually look at the US population model for both exponential model and a logistic model. Right? So let's look at the exponential model, which we know quite a bit about. Right. So in the year since 1790, so in 6 years after 1790, the model is pretty nice using exponential growth, but exponential is actually not that it's not going to fit well when the time expands when we look at maybe 100 year or 150 years. Right. So on the right hand side, we can see that we have the logistic model 150 years after 1790, right? So you can see that this model actually fits pretty well, a little a different form than the exponential growth model, right? So in this case, in this section, we are going to focus on how do we work with a logistic model. All right, so this is the basic logistic function. Has the form you use capital P for population, which is what we're going to use a logistic model mostly for. The function is equal to capital L over 1 plus C times e to negative kt, where L, C, and K, they're all constants. And then we're going to look at first how these constants will affect our graph. Okay, so let's look at our first example. Consider the logistic function capital P equals to L over 1 plus 100 e to the negative kt. All right, we have two parts here. So in this example, we're just going to analyze the graph and see what these different parameters does to the graph. All right, so part A, we're going to let k be equal to 1 and graph P for several values of L and explain the effect of a parameter of L. So in this example, let's do L equal to 1, 2, 3, and 4. And let's graph these out using a software or an online calculator. All right, so here is the graph using software, and this is actually from our textbook. All right, so you can see that if we let k be equal to 1, right, so we have negative e to the t right here, and then L on in the numerator. So notice that the effect of L here actually, when L is 1, we have this line line right here, right? And when L is 2, we can draw lines like this, right? So L, the value of L actually determines the upper bound for the function, right? So let's write it out. The parameter L determines the horizontal asymptote and the upper bound for P. Okay, so upper bound meaning right where the function is going to go to as we increase the value, right? So when L is 1, notice that the line is increasing, but then when it gets closer to P equal to 1, it flattens out and then keeps going. It doesn't look like it's going to go over 1. And then so on with 2, 3, and 4. Right. So here, the parameter L is acting as a horizontal asymptote and an upper bound for the population. All right, and let's now look at part B. Part B, we're going to pick L equal to 1 and look at several values for K, right? Different values for K. And we're going to see what K does to the graph. So here we go. All right. So the first thing that you can see, L equal to 1, that's your horizontal asymptote or the upper bound, right? Because we pick L equal to 1. That's what the effect that we have by picking L. All right. So we can see that when K is small, it's increasing gradually, right? It's not increasing that fast. right? And when k is large, notice that it shoots up really fast towards the upper bound and then flattens out real fast, right? So when k is large, it increases rapidly, right? So what does the value of k, how does it affect our function? So the perimeter k affects the steepness of the curve, right? When k is large, it's really steep because it's increasing very fast. Now, notice that in these two examples, the functions are always increasing, right? Whether it's slowly or fastly, but it's always increasing, right? So logistic function is always increasing, right? And notice that if you look at any, let's look at L4, right? So for the first part, looks like from here, it's concave up, right? It's like a cup. And then somewhere in here, it becomes concave down, right? So a logistic function is always increasing, concave up first, and then to concave down, right? And there is always a point of inflection in between, right? There is always a point of inflection, right? Remember the definition for a point of inflection? That is the point where the function changes concavity, right? It's point where the graph changes concavity. All right. So L determines your horizontal asymptote and upper bounds, and K determines the steepness or how fast your function is increasing. All right, next let's look at some properties of a logistic function. So first, we're going to look at the value L, right? So the value L is actually called the carrying capacity for P, right? What's the in terms of population, right? What is the max population that we can have in a place, right? For example, at on campus, right? How many students can we have on campus? Is there a capacity, right? I know there's one in a different classroom, right? So P is the capacity, right? The max number that you can have. Here it's working as an upper bound as well as a horizontal asymptote, right? As we saw from earlier. All right, next, the point of diminishing return is the inflection point where P is growing fastest and it occurs where P is equal to L over 2, right? So here, L over 2, that is your point of inflection, right? And point of inflection, and it mentions here in the notes, right? It's where it's growing the fastest. Okay, so that's important to keep in mind, right? Uh, where the graph changes concavity, L over 2, the point of inflection is the where P is growing the fastest. Okay, and you can see that below the point L over 2, the graph was concave up, means it's increasing faster and faster. But after this point, it's still increasing, but notice that it's increasing slower and slower and slower as it flattens out. Right, so that's what the point of inflection does is it shows you where the graph is increasing or decreasing the fastest. All right, and last, the logistic function is approximately exponential for small values of t with growth rate of k. Right, so for small values, we can, if you just look at like a little part and it looks like an exponential graph, right? But for small values of t, it looks like an exponential function, right? And then you can actually look at this form, right? We have c times e to the negative kt in the denominator. If they were in the numerator, then you will have c times e to the negative kt, to the kt, positive kt, right? Which will show us it's an um, exponential growth type of model. All right, let's look at this example together. We have T is in years since 1790, P in millions, and we're using this logistic model to model US population between 1790 and 1940. According to this function, what is the maximum US population, right? So we talked about this earlier. L is max capacity, right? Right. And that's usually like the upper bound or how high we can go. So in this case, L is equal to 192. That means 192 million would be the max U.S. population, and which we know might not make sense, right? We U.S. has a really big territory, and then more people are being born, and more people are immigrating to the U.S. All right, so part two, is this prediction accurate? And how does this logistic model fit the growth of U.S. population since 1940? All right, so let's take a look at a graph that goes with this problem. All right, so here is the graph for our logistic model P, with represented by the blue line. All right, and the black dots are the actual population for the U.S. Since 1790 to t equal to 220, which is the year 2010. So you can see that before right here, right, in this part, it's pretty accurate, right? Pretty accurate, right? And you can see that after here, it still just keeps on increasing and increasing. And so let's answer the question: is this prediction accurate? Well, it wouldn't be accurate like towards the end, right? But it's pretty accurate in the beginning, the first few years, right? The first few hundred or under some years, it's pretty accurate. How well does this logistic model fit the growth of U.S. population in the year 1940? All right, so in the year 1940, we should be expecting some somewhere around here. It's 1940, right? So 1940, besides the World War, and of course towards the end of World War II, there's a boomer, right? Baby boomers. So we do see an increase, a rapid increase in population, which was somewhere about right here, I want to say. Right. So even though after that we still see a rapid increase in in the population, right? So yeah, for small t values or lower t values, logistic model is really accurate, fairly accurate, actually more accurate than exponential in the beginning, right? But as later on we see that it still keeps on increasing, right? So the max capacity of 192 million might not work in this case, right? Let's say if we change the max capacity to something else, like say 300, 400, or 500 million, right? Even 100 million, three even 1 billion, right? So it's possible that we get a lot of people in there, and maybe in that case we can do switch some values around and make a better logistic model for the US population. All right, so based on the model, right, um if we want to find the point where concavity changes, right? So L over 2, which is what 96 mil, right? 96 million. That's about here, right? About here. Right. So we can see that the model, the blue line is about a point of inflection where it starts to change concavity, and we can see that the population is increasing quite rapidly here. well, of course, not as rapidly as later on in the years, but we can see we can see that according to the model, the data is actually acting fairly accurate up to this point. But after that, there are things happening. Boomers, more people coming into the country, immigrated to the country, and then we see a sudden increase in the population. All right. Okay, so here is another example 4 from the textbook, actually. I just want to talk about a different example and working with a logistic equation. I think this example is quite fun to look at. So we have 3 types of drugs, and what are the advantage and disadvantage of each drug? All right, so let's just break it down with A, B, and C. Okay, so notice that we have the dash line here, maximum safe response and minimum desired response. So we want the drug to at least hit the minimum desired response, meaning the drug has to work in some way. And the maximum safe response is we hope that the drug doesn't exceed any safety concerns that people have. All right, so part A, we have pros. um, it's very effective, right? You take little dose and then it will go over the minimum desired response very fast. But it also might increase over your safe response real fast as well. So pros, we can say fast response, fast response time, right? And the cons might be might go over the safe response too fast. Might go over safe response, right? Might go over safe response, right? And we can see that part drug B also has the same capacity as drug A, meaning it's gonna work, but it will take a little more dose to hit the minimum desired response, and then it will take more dose to go over the maximum safe response as well. So drug B is a little slower than A, but in terms of dosage, it's a little safer because you have more time to react before you hit safe response. All right, so pros, um, more time to react before going over a safe response. And then cons can be um, um, needs more dosage to hit desired response. I know this is not like a medical class or anything like that, but it's fun to look at things like this. All right, where drug C, it's just very slow, but notice that it will never go over the safe response. So pros, always safe, right? Max capacity is below max safe response. But the cons, you need a lot of dosage, right? Need even more dosage than drug B. Okay, so logistic model can also be used in this way to test the effectiveness of drugs. Um, in this case, we'll probably say that drug C may be the preferred drug despite the lower maximum effect, right? But it's safer, right? And even though you need a little more dose, but it's safe, and that's what we would probably prefer, right? We don't want to take the chance of going over maximum safe response and then having something happen to the people who are taking these drugs. All right, so that's 10.7. Most of the section is just to analyze the function, analyze the graph, and answering some question. Of course, we have some properties over here. Make sure you have that in your notes. And yeah, that's it for 4.7. And thank you guys very much. See you next time.